Hello viewers, in this session we will solve some problems based on the theory we have seen so far. So, like before, I encourage the viewer to solve as many exercises from the textbook as it takes to gain confidence in the subject matter. So, here I will be able to solve a few problems which will sort of use the theory which I have discussed so far. So, after each question that I present here, the viewer is encouraged to pause the video and try to solve it by himself or herself, okay? And then you can look at the solution that I present here. Okay? So, let us start with the following question. This question is sometimes called the minimum modulus theorem, okay? So, or a version of it. So, let f be analytic and non-zero in a region A. Okay. Show that the modulus of f, okay, has no strict local minima on A. Okay. So, the solution is here. Okay. Since f is analytic and non-zero, more importantly non-zero, okay, in A, 1 by f is, so you can consider the function 1 divided by f which is non-zero. So, there is no 0 in the denominator. 1 by f is also analytic in A. Okay. Now, by the maximum modulus theorem, okay, we know that the modulus of 1 divided by f, okay, has no maximum on the open set, okay, on the open connected set A. Okay. If the modulus of 1 by f has a maximum, that has to occur at the boundary of A and not at any interior point of A, that we showed. Okay. So, this has no maximum on A. So, what this means is that f has, modulus of f has no strict local minimum at A, okay, on A. Okay. So, this is easy. So, the next question is as follows. By the maximum modulus theorem, we know that if we consider a entire function and a bounded set, okay, then the entire function will have its maximum modulus somewhere on the boundary of the bounded set. Okay. So, here is a question to find, okay, so find the maximum of the modulus of sin z on 0 to pi cross 0 to pi. What that means is the x variable is within 0 and 2 pi and the y variable is within 0 to pi. Try to answer this question and I will present the solution here. Okay, the solution is as follows. So, when you look at the sin z, sin of x plus I y, this is equal to sin x cosine h y. It should be cosine I y, but we know that cosine I y is cosine h hyperbolic cosine y, okay, and plus cosine x sin I y, which is I sin hyperbolic y. So, I sin hyperbolic y times cosine x, okay, right. So, the modulus of sin x plus I y is going to be a simple calculation shows this is going to be sine squared x cosine h squared y plus sine h squared y cosine squared x. Okay. Okay. So, this is equal to sine squared x times 1 plus sine h squared y plus sine h squared y times cosine squared x, which is equal to sine h squared y times sine squared x plus cosine squared x plus sine squared x, which gives us sine h squared y plus sine squared x. Okay. So, now sine squared x we know is between 0 and 1. Okay. So, sine squared x is at most 1, okay, and sine squared x is equal to 1 when x is equal to pi by 2 or 3 pi by 2, okay, in this interval 0 to pi. Okay. So, now the maximization problem just boils down to the maximization of this function, okay, and we know that the maximum occurs only on the boundary of this region, the square region 0 to pi 0 to pi. Okay. So, we are only interested in inspecting on the boundary region where this expression attains its maximum. Okay. So, we can look at sine h squared y. Okay. Sine h squared y is an increasing function. Okay. So, sine h y is an increasing function. Okay. That is because cosine h y, its derivative is never 0, it is actually positive, strictly positive. So, so sine h y is always an increasing function and attains maximum at y equals 2 pi. In the interval 0 to pi, its maximum is obviously at 2 pi. So, at y equals 2 pi you have a maximum. So, sine z on the modulus, okay, has a maximum at the point pi by 2 comma 2 pi, okay, or 3 pi by 2 comma 2 pi. So, what I mean by this is a point in the complex plane 2 pi belongs to C. Okay. So, that is the maximum of sine z modulus. So, the next question is the extended Liouville's theorem. Okay. So, suppose that f is an entire function and if for some integer k greater than or equal to 0, okay, there are positive constants a and b such that modulus of f of z is less than or equal to a plus b modulus of z power k. That inequality is true for any z belongs to C. Show that f of z, okay, is a polynomial of degree at most k. Okay. So, we are calling this the extended Liouville theorem because when k is equal to 0, you are saying that the modulus of f is bounded by a positive real number. Okay. So, then we know by Liouville's theorem that this is a constant function. So, f is definitely a polynomial of degree 0. Okay. So, now we can extend this to any k, any integer k which is non-negative. Okay. Please try to solve this exercise and I will present the solution here. What one does is one proceeds by induction, because we need to do this for every positive non-negative integer k. Okay. So, notice that k equals 0, okay, the statement is true. For k equals 0, okay, the statement that f is a polynomial of degree at most k is true for k equals 0 by Liouville's theorem. Okay. Now, that is nothing but the Liouville's theorem. Okay. So, now suppose that okay, under the given hypothesis, okay, the statement is true, this statement is true, of course, only under the given hypothesis, okay, for any k, okay, less than or equal to or strictly less than a particular integer n. Okay. So, n a non-negative integer. So, we are going to show that the statement is true for n itself. Okay. So, define h of z to be a split function f of z minus f of 0 by z for z not equal to 0, okay, and define this to be f prime of 0 at z is equal to 0. H of z we define it to be this kind of split function. Okay. So, we will show that f h is entire. Okay. So, first notice that f has a Taylor series expansion around 0, which is valid on all of the complex plane, because f is entire. F of z can be written as f of 0 plus f prime of 0 z plus f double prime of 0 by 2 factorial times z squared, etcetera. Okay. And this is valid, this expression is valid for all z belongs to C, because f is entire. Okay. And from this we can calculate that f of z minus f of 0 by z is equal to f prime of 0 plus f double prime of 0 by 2 factorial z squared plus so on, sorry, z here, plus let me go one more expression f triple prime of 0 by 3 factorial times z squared plus so on for z belongs to C minus 0. Okay. For C minus 0, because we are dividing by z, f of z minus f of 0 is this expression. Okay. So, this power series, this is a power series. Okay. So, this is what we are defining h of z to be is analytic. We showed that the power series are analytic. Okay. So, analytic on C minus 0. In fact, by defining h of 0 to be f prime of 0, okay, we have made it analytic on all of C. Okay. So, h of z is actually analytic. So, h of 0 is equal to f prime of 0 if we consider this h. Okay. So, so h is analytic, okay, is entire actually. Okay. So, the definition of h of z as f of z minus f of 0 by z is precisely this kind of definition, except at 0, and at 0 we have remedied the situation by defining it to be f prime of 0. Okay. So, h of z is precisely this power series which is valid on all of the complex plane. Okay. So, h is entire. We can now use the induction hypothesis. Okay. So, h is the modulus of h, notice, is now going to be the modulus of f of z minus f of 0 by z. Okay. So, firstly the modulus of h of z is bounded on the unit disk, the closed unit disk. The closed unit disk right. That is because h is continuous, h is entire function, it is analytic. So, h is continuous. So, the modulus of h is continuous function, a continuous function on compact set is bounded. Okay. So, modulus of h of z is bounded. Okay. So, let modulus of h of z be less than or equal to m for z belongs to the closure of B 0 1. For z such that the modulus of z is strictly greater than 1, what we have is the modulus of h of z here is equal to the modulus of f of z minus f of 0 by z. Okay. So, the modulus of this is less than the modulus of f of z by z plus the modulus of f of 0 by z. Okay. And we know that the modulus of f of z by z is less than the modulus of a plus. So, here let me go to the question. The question says the modulus of f of z is less than or equal to a plus b mod z power k. So, I will use that. So, the modulus of f of z by z is less than or equal to a plus b mod z power k, okay, divided by mod z, okay, plus modulus of f of 0 by z. Okay. And since this is strictly less than or this is less than or equal to a plus modulus of f of 0 by modulus of z, okay, and then plus b modulus of z power k minus 1. Okay. So, which is less, I mean this is a constant, okay, and modulus of z is greater than 1 tells that 1 by mod z is less than 1. So, this is less than a plus modulus of f of 0, okay, plus b times modulus of z power k minus 1. Okay. And by the induction hypothesis, this is some other constant c. Okay. So, by the induction hypothesis, by this statement here, okay, we know that h has to be a polynomial of at most degree k minus 1. Okay. So, by induction hypothesis, h is a polynomial of degree at most k minus 1. Okay. So, going back to the definition of h. Okay. So, z times h of z plus f of 0 gives f of z. So, f has to be a polynomial of at most degree k. Okay. So, f of z is equal to z times h of z plus f of 0 is a polynomial of at most degree k. Okay, and that proves okay, what our contention is. Okay. So, that shows that f is a polynomial of at most degree k. So, the next question is as follows. Okay. So, find the power series expansion of the function 1 by z squared minus 3 z plus 2 about 0. Okay. Find the radius of convergence. You can pause the video here to answer the question yourself. Okay. And here is the solution. Okay. So, 1 by z squared minus 3 z plus 2 can be written as, well, we will factorize z squared minus 3 z plus 2 as z minus 1 times z minus 2. Okay. And we observe immediately that the denominator is 0 at 1, okay, and 0 also at 2. Okay. So, if you are going to determine a power series expansion around 0, okay, the function encounters this point 1. So, when you go in circles outwards of 0, there is a certain resistance at this point 1. okay, where the function is not defined. Okay. Later when we study singularities, we will call such a point a pole, okay, in this case a simple pole. Okay. But in any case, this the Taylor series expansion of this function about 0 can have a radius of convergence at most 1 from this kind of picture. Okay. So, we will also show that directly, okay, without resorting to this kind of picture. Okay. So, 1 by z minus 1 times z minus 2 in order to write it in the form of power series about 0. Okay. What we will do is split this into partial fractions. Okay. So, when we split this into partial fractions, we get 1 by z minus 2 minus 1 by z minus 1. Okay. And what we will do is expand 1 by z minus 1 and 1 by z minus 2 independently as power series. Okay. So, this gives us this is equal to 1 by 1 minus z. Okay. So, I am taking this term first, okay, and converting that to 1 by 1 minus z plus or rather minus 1 by 2 minus z, okay, which can be written as 1 by 1 minus z minus a half times 1 by 1 minus z over 2. Okay. And 1 by 1 minus z we know has an expansion around 0, Taylor series expansion around 0. It is a geometric series z power n equals 0 through infinity, minus half times the expansion for 1 minus z by 2 likewise is a geometric series n equals 0 through infinity of z by 2 raised to n. Okay. And this series is equal to this function. Okay. This is valid only for modulus of z strictly less than 1, okay, like we have remarked here in the picture. Okay. So, this picture appears in this statement, okay. And likewise this expansion, this function is equal to this expansion only if the modulus of z by 2 is strictly less than 1, okay, which means the modulus of z is strictly less than 2. Okay. So, this difference, so the difference of these two functions is equal to the difference of these two series if and only if both the series converge, which means converge to these functions, okay, which means this series expansion is valid only on the intersection of these two sets, set of all z such that mod z is strictly less than 1, intersection set of all z such that mod z is less than 2, okay, which is simply the set mod z is strictly less than 1. Okay. On the disk of radius 1 on the unit disk, okay, open unit disk, this expansion is valid, okay, n equals 0 through infinity z power n minus half times this. Okay. So, now let us try to put these two series together by collecting the coefficient of z power n in either. Okay. So, this gives me 1 minus 1 by 2 times 1 by 2 power n, because that is the coefficient of z power n, and so this is sigma n equals 0 through infinity z power n times 1 minus 1 by 2 power n plus 1. So, that is the power series expansion of this function around 0, okay. And this is valid for mod z strictly less than 1. So, that is the solution to this problem. Okay. On to the next question. So, let f of t be a complex value continuous function defined on a real interval a comma b. Okay. So, it is a function of a real variable, complex valued function of a real variable. Show that the Laplace transform capital F of z is equal to integration from a to b e power minus z t f of t dt is entire analytic for any z belongs to C. Okay. So, you can pause the video here to answer the question yourself, and here is the solution. So, what we will show is capital F is differentiable for every z in the complex plane, okay, and that will show that capital F is analytic. Okay. So, let us consider the difference quotient, let z belong to C. So, we will fix a particular z, okay, f of z plus h minus f of z divided by h. Okay. Here h is a complex number, okay. H we will later make it tend to 0. Okay. So, h belongs to C. Okay. We can assume h has a small modulus if needed, because we will eventually take the limit of this quotient as h tends to 0. Okay. So, this is equal to the integration from a to b, okay, of e power minus z plus h t, okay, f of t dt minus integration from a to b of e power minus z t f of t dt, okay, divided by h. Okay. We will simplify this. Well, firstly this is integration from a to b e power minus z t e power minus h t f of t dt minus integration from a to b e power minus z t f of t dt, okay, divided by h. So, this is 1 by h times all of this. Okay. So, this is 1 by h times, well, I will combine these two integrals a to b e power minus z t f of t times e power minus h t minus 1, okay, times dt. Okay. And I will write this again as, since h is independent of the integration, I can take h inside of integration, okay, and then e power minus z t f of t e power minus h t minus 1 by h dt. Okay. So, here now one can, after this basic calculation, okay, one can see that this expression which is inside the integration, okay, can be likened to the derivative of the function e power minus z, let us say, okay, provided we have a t in the denominator here, etc. Okay. So, one then encounters a problem, because t could be 0 in this interval a b. Okay. So, there are two cases. Okay. So, for the time being, let us take the simpler case. Okay. So, suppose 0 does not belong to the interval a b. Okay. This is the easier case. So, if the interval a b is off of 0, what we can do is, then this is equal to, so then let me take the limit as h goes to 0 of f of capital F of z plus h minus capital F of z by h. That is going to be the limit as h tends to 0 of this integral a to b e power minus z t f of t e power minus h t minus 1. Okay. So, then I am going to multiply and divide by t. Okay. I can do that because now 0 does not belong to the interval a b. So, t cannot be 0. So, I can multiply and divide, and then this, since the limit h goes to 0 does not depend on t, I can take the limiting process inside the integral. Okay. So, this is integration from a to b e power minus z t f of t times limit as h goes to 0. Well, if h goes to 0, h t also goes to 0. okay, of e power minus h t minus 1 divided by h t times t dt. Okay. And we know that e power letting z or I think I use z w equals h t. Okay. W tends to 0 as h tends to 0. Okay. We have limit as h t goes to 0. Okay. This limit is equal to so this limit I will just say that limit is equal to limit as w goes to 0 of e power minus w minus 1 by w. Okay. And that is the derivative of e power minus w at 0. Okay. So, this is nothing but minus e power minus 0, which is minus 1. Okay. So, with that I have this is equal to so this is all in parentheses. So, this is equal to integration from a to b minus t e power. So, I am taking this t here minus t e power minus z t f of t dt. Okay. So, the derivative exists, and so if 0 does not belong to this interval a b, I have shown that f is entire. Okay. So, f prime of z is equal to minus integration from a to b t e power minus z t f of t dt, and okay, for each z belongs to C, and hence capital F is entire. Okay. Now, in the other case where suppose 0 belongs to a b, then what one does is one considers this integral by splitting the integral at 0 and taking the limits of okay. So, I will explain that f of z is equal to so suppose 0 is in there. Okay. So, f of z can be written as limit as I want to pick s tends to 0 of integration from a to s of e power minus z t f of t dt, okay, and plus limit as s tends to 0 of integration from s to a b, okay, e power minus z t f of t dt. Okay. One then uses what we have already done to conclude that this is this right here, okay, and this once again is this right here, okay, with s and b as limits, okay, and then one can club the two integrals, because now in the end after the derivative process, okay, you can have you can club these two limits, okay, to get the integration from a to b of this expression. Okay. So, what I mean is this is independently integration from a to b minus t e power minus z t f of t dt limit as sorry a to s, I apologize, limit a to s goes to 0 plus limit as s goes to 0 integration from s to b minus t e power minus z t f of t dt. Okay. So, we will delay that limits. Okay. So, f prime of z will be that, okay, and that can now be combined a to b minus t e power minus z t f of t dt, because now there is nothing improper about combining these two definite integrals into this one. Okay. So, that is the other case. So, that shows that f is entire in any case, okay, capital F is entire. Okay. So, that is okay, and I will put one more question to the viewer. Okay. So, if f is an entire function, an entire non-constant function, okay, show that the range of f is a dense subset of C. Okay. So, to show that it is a dense subset of C requires some more work. Okay. So, it is an exercise. So, the next question is as follows. Suppose that f and g are analytic functions on a region omega contained in C, okay, and that f times g is identically the 0 function, okay, the constant 0 function on the region omega. Okay. Then prove or disprove the following. Either under these circumstances, either f is identically 0 on omega or g is identically 0 on omega. Okay, so, that is the question, and try to solve it yourself, okay, and I will provide the solution here. So, the idea is to use the identity theorem. Okay. So, what is important is that if f is not identically 0, okay, then its zeros are actually isolated. Okay, that is the identity theorem. Okay. Notice that such a feature is not available for functions of real numbers. Okay. A differentiable function can be 0 for a while on the real line and then suddenly have a non-zero value or a pickup from there and have non-zero values beyond a point. Okay. So, but that is not the case for functions of complex numbers or analytic functions of complex numbers. If they are 0 on a set containing a limit point, then they are identically 0 on the whole region of analyticity, okay, on the region of analyticity as long as that is connected. Okay. So, that is true for analytic functions. Here now what we will do is we will suppose that f is not identically 0. If f is identically 0, then this statement is already true. Okay. So, let us suppose that f is not identically 0, then let us see what happens. Then the zeros of f are isolated. Okay. We have examined the zeros of analytic functions, and this is our conclusion from that. Okay. The zeros of f are isolated. Okay. And since they are isolated, okay, so let z naught belong to omega. Okay. F possibly could be 0 there, or it is possibly non-zero there. Okay. Whatever that is, we know that there is a neighborhood of z naught, okay, in omega, such that f is not 0, okay, in that neighborhood, in the deleted neighborhood. Okay. So, in the deleted neighborhood of z naught. Okay. More specifically, we know that there is an R positive, okay, by the properties of the isolated zeros of analytic functions, that or by continuity of f. Okay. So, there are two cases. If f of z naught is 0, okay, then we know this by the isolated zeros of f. Okay. And if f of z naught is non-zero, then we know by the continuity of f that there is a R positive such that B Z naught R is contained in omega. Okay, this is by the openness of omega. Okay, and B prime f of z is non-zero for z belongs to B prime of Z naught R. Okay, so that is true. If f is 0 at Z naught, then this is true because the zeros are isolated, and if f is non-zero at Z naught, then this is true by the continuity of f in B Z naught R. It is analytic, so it is definitely continuous in B prime Z naught R. Okay. So, that is true, we know there is such an R, and since f is non-zero in there, okay, but f times g is identically 0, but f times g is identically 0 in on omega. So, in particular we are left with no choice but to say that g of z is equal to 0 for any z belongs to B prime Z naught R, because f is non-zero there. Okay. So, what that tells us is that g, the function g is 0 on a set with a limit point. Okay. So, notice that this is an open set. Okay. So, every point in B prime Z naught R is actually a limit point. Okay. So, in particular g of z is 0, okay, on a set with a limit point. So, by the identity theorem we know that so g is identically 0 on B prime Z naught R. Okay. And since omega is a region, okay, we know that it is connected, okay, and on a portion of it, on a set containing a limit point, okay, g is identically 0 on it, okay, which is contained in omega. Okay. So, since omega is a region, g is identically 0 on all of omega by the connectedness of omega, okay, since omega is connected. Okay. So, that shows that this, if we suppose that f is not identically 0, then g has to be identically 0, which proves this statement. Okay. So, that is a solution to this problem. Let E be a non-empty subset of C. Okay. Define f of z to be the infimum of modulus of z minus w such that w belongs to E. Okay. So, the infimum is taken over all the points belonging to E, okay, for a z belongs to C. For a given z belongs to C, you define f of z to be this. Okay. Show that a f of z is continuous function, okay, continuous function on all of C, okay, in C, and B, show that f of z is 0 if and only if z belongs to the closure of E. Okay. So, this is a question the viewer is asked to solve, okay, and then there is yet another question that I will put here. Okay. So, suppose f is analytic, let f of z be analytic function in the unit disk. Okay. Define g of w to be f of z, where W is T of Z, okay, and T is a Mobius transformation okay, mapping the unit disk to unit disk, or rather unit disk conformally onto itself. Okay. Then show that the 1 minus the modulus of W squared, okay, times modulus of d g by d W is equal to 1 minus the modulus of Z squared times modulus of d f by d z. Okay. So, you have to use the chain rule to arrive at the solution. Okay. So, please try this problem. Okay. Also of interest is the following. Okay. It is very useful and important problem. Find or give an expression. Okay. So, I will maybe give it as a show that. Okay. Show that T such that T of D is equal to D, okay, where D is the unit disk, unit B 0 1. Okay. Okay, has the form, has the general form T of Z is equal to e power I lambda times Z plus alpha by alpha bar Z plus 1, okay, where lambda is a real constant, okay, and alpha belongs to B 0 1. Okay. So, the set of all transformations which take the unit disk onto unit disk, that equality means that it takes unit disk onto unit disk, has the form e power I lambda times Z plus alpha divided by alpha bar Z plus 1. Okay. So, this is also an exercise for the viewer. All right. So, with this I will stop this session here. Okay. So, the viewer is asked to solve more exercises and try to gain good understanding of the theory via the problems as well.